Hi, I'll be starting the session in next 10 minutes. There's some network glitch we're trying to solve.
Visible. So this is NPTEL PMRF live session 8. So in this session, we will be talking about the quality of service, which is the covered at the network level. So then now we have studied about the network here and
Okay, sorry, I think my voice was not audible earlier. So I think now it's audible. So we are today having the session 8, which talks about the network layer protocol and also the quality of service which is provided at the network layer. Okay, so what does the earlier we have studied about the network layer and what are the things being or what are the protocols conducted at the network layer and the services provided by the network layer. So let us have a quick go with the last previous week's assignment. So I think we have skipped the previous session. That session I'll be having today, and then after today I'll be having the concurrent session on 24th. So I'll continue from where we have left in the previous section. So here are a few questions. So I would like to first attempt all of you to attempt those questions, and then we will see like what are the next things we will be covering in this session. That is regarding the quality of service that will be covered in this session. Okay. So I would love if everybody would respond to the questions because you all have attempted those. So question number 1 is that if network address translation device runs out of addresses, that is no address is left in the pool configured, then the packet will be dropped. And the Internet Control Message Protocol, that is ICMP, host unreachable packet is sent to the destination. So is it true or false? I would ask everyone to please answer the question. Is it true or false? Okay, so the answer is true. That is the ICMP protocol. Host, and if host is unreachable, packet is sent to the destination and the packets will be dropped when NAT runs out of addresses. So the next question is, what is supernetting? Is split a large network into multiple small networks or combine multiple small networks into single large network, enable the network to accept more hosts, or connect a new network to an existing network. The correct answer is B. That is to combine multiple small networks into a single large network. That is called supernetting. The next question is, what is the maximum number of networks possible in class C IP address? Yeah, so I'm just asking the questions, and this one is the question that I have presented. What is the maximum number of networks possible in class C IP addresses? Yeah, so you know that how many bits are allotted to class C IP addresses? So according to that, the answer is C. That means 21 bits are allotted. So class C IP address is divided into 32 bits into two parts. One is the network ID, that is the 24 bits, and one is the host ID, that are the 8 bits. So in class C network, the first 3 bits are fixed. Similarly, in class B network, first 2 bits are fixed, and in class A network, first 1 bit is fixed. So the remaining bits, 20, that is 24 minus 3, that equals to 21, are used for the network ID generation. So the total of networks possible in class C is 2 to the power 21. So I hope everyone gets it. Can you respond? Is the voice audible now? Okay, thank you. Right. So the next question is, uh, which of the following is not a valid IPv6 address? I think the answer is very obvious to you. These are the four IPv6 addresses given. So please give me a conceptual answer, like which of the following you think is not a valid IPv6 address. Okay, so you given the answer as D. This is not a valid IP address. That's true. But IPv6 addresses must there are some specific rules and formats given this given the given address D is not a valid IP address because it does not contain the required number of groups or colons separated by hex quarters. That means we said that we can put a double colon or we need, I mean, at least one side a double colon to express the length of the zero, but it should it is not having a double colon. That means it is a group of only four separated groups separated by four colons. However, this IPv6 address is separated by eight colon. That means it is separated into eight groups by the colons. So this is missing in this case. That means it is not a IPv6 valid IPv6 address. So the next question is, which is true for class E? Okay, yeah. So the correct answer is B, that class C IP addresses are reserved for experimental purposes. Question number 6 is the header length of IPv6 datagram is 10 bytes, 20 bytes, 30 bytes, or 40 bytes. Yeah, so I think you have answered it right, that the length of IPv6 datagram is 40 bytes. So next question is, by the help of NAT protocol translation technique, IPv4 and IPv6 network can also communicate with each other, which do not understand the address of different IP versions. True or false? Yeah, so the correct answer is that is true. By the help of NAT protocol translation technique, the IPv4 and IPv6 networks can also communicate with each other, which do not understand the address of different IP versions. Okay. Yes. So the next question is, we write the IP address as 191.180.83.235/12 in CIDR notation, which is what is the subnet mask for this particular IP address? I think we are all clear. This is a question of supernetting and subnetting. So according to that, what is the subnet mask? So the correct answer is A, that the first 12 bits are the network address, and the rest bits, that is 32 minus 12, are the 20 bits that are used for the host address. So for IP 191.180.83.235, binary value is 1011111111. Okay, till the and this is the binary value allotted to this. So for this, the subnet mask is 10. And this, like, all the initials are for the sorry, the initial, yes, so the initial 12 bits are for the network ID, which are assigned as 1, and then the remaining bits are assigned as 0, that are the 20 bits. So accordingly we give the subnet mask. So what is the maximum number of hosts under class B addresses? The maximum number of hosts under class B, as we mentioned, that 16 bits are allotted for the network ID, where 2 bits are reserved, and the remaining 16 bits are for the host ID. So the possible combination of hosts are 2 to the power 16. However, there are two addresses of hosts which are allotted, that are the highest on the and the lowest, which are reserved for particular purposes. That is the host ID and the broadcast, that is the network ID and the broadcast ID. So we remove those two. So the total number of possible host under class B addresses are 65534. So everybody, I think, understood this concept till now. So the last question is that if the direct broadcast address of the subnet is 201.15.16.31, which of the following will be the subnet mask? Please calculate and tell me. Okay, so the correct answer I'll say is A, that is direct broadcast address of subnet this is 201.15.16.0.0. Here for this subnet mask, for this can be this. And then subnet mask for this particular address can be this. And the subnet mask for this particular address can be this. So accordingly, we choose that A is the best is the possible subnet mask for this particular direct broadcast address. Okay. So now let us start with our lecture of today, which talks about the quality of service mm, of the application. So the internet, like we have provided the proper bandwidth, or we have provided the proper network, we have sent the data. However, what is the quality of that data, or what is the quality of that particular service? If we are playing a video on the YouTube, however, that video keeps on buffering for a long duration of time, and you are not able to see that video of 30 minutes even within 2 hours. So that will be extremely low quality of service for the user or for the person who is watching that particular video or accessing that application. So to maintain the quality of service, there are various factors, and what exactly is the quality of service that we will be covering in this particular lecture. Okay. So, firstly, we are revisiting congestion. As I mentioned, like there is a buffering in the YouTube. So that means there is congestion at the backend. So does the TCP congestion control ensures no congestion in the network? Like, I will ask you this question. Like, we have studied till now the TCP congestion control. So you all might be aware of it. So can you answer that? Does the TCP congestion control ensures no congestion in the network? Is it the case? Or there is still congestion in the network if the TCP congestion control occurs? All of you, please give a response. Like, what do you understand by this? Like, I think everybody is now aware of the TCP congestion control. And does it controls the congestion, or there is no congestion at all? Okay, so it controls the congestion. That means that there is no congestion in the network that is not ensured by the TCP congestion control. There is the case in TCP congestion control that the congestion has already occurred, and after the occurrence of that congestion, we try to avoid that congestion or how to cure from that congestion. So how does that congestion impact the network performance? So we have seen there are various factors which are contributing in impacting the network performance. So the congestion can be due to the bandwidth problem, that the proper bandwidth is not allocated to the particular network. So there is a congestion in the network and the packets are not able to transmit. The next possible case is the delay, due to which for example, if a packet gets lost on the way or there is a congestion, so there will be a delay in the transmission of the packet. And third, due to the congestion, there might be a jitter. So you might be knowing of delay and bandwidth. So what exactly jitter is? Jitter is the variation in the delay of the packets which are sending. So there might be a case that some packet is has been sent in 20 seconds and some packet is sent in 10 seconds. So the delay amount for one packet was something else and the delay amount for another packet is something else. So that is the delay variation is known as jitter. And fourth case is the packet loss, that the packet gets completely lost and it is not reaching from the server to the client or client to the server. So now we'll see individually the terminologies, how they are impacting the this quality of service. Okay. So amount of data that what is network bandwidth? So network bandwidth is the amount of data that can be transmitted over a link within a fixed amount of time. Given a particular time, what is the amount of data which is being transmitted is known as the network bandwidth. So it is said that when a drain chronically runs slow, even though isn't plugged, it's time to get a bigger pipe. So that means there is a pipe which is having a lot of uh, yeah, wait. Yeah, so there is this pipe which is having this space. However, the data coming is more than the size of that pipe. So there is a congestion, and this can be termed in a normal day to day. So we need a bigger pipe. So when we are draining something out of our homes or there is a drainage system, so there is a possibility that sometimes that drainage system gets blocked because there is a lot of garbage which is being pushed to that drainage system and that gets clogged in that drainage system and it is not able to push that huge amount of the garbage. So for that system, we need to make the size of that pipe bigger. So that is what quality of service is controlled by giving more bandwidth. So some applications in the network are bandwidth hungry, that is the video application. So congestion limits per user bandwidth. So how to improve the bandwidth is by using the design networks with higher capacity. Okay. The next component is the delay, which is impacting the quality of service. So there are three components in the delay. One is the transmission delay, second one is the propagation delay, and third one is the queuing delay. So what is the transmission delay? Transmission delay is the amount of time to push all the packet bits in the network. That means, for example, the bandwidth say is 8 Mbps and the packet size including header is 1 MB. So the total transmission delay, that is the time to push all the packets, will be 1 second. So the packet size is 1 MB and it is taking 8 Mbps. The total time it is, for example, if we have to transmit 8 packets, it will take 1 second of time. So the time which is taken to push all the packet bits into the network is known as the transmission delay. The next terminology is the propagation delay. That is time to transmit one bit from one end of the link to another end of the link. it usually depends on the underlying communication media. So there is a difference between transmission delay and propagation delay. Transmission delay is that the how many packets you push and what is the capacity of that particular pipe. So accordingly, how much time it takes to transmit from here to here to push all the packets. However, propagation delay is the time taken from transmitting from here to here. In between, something occurs or there is any problem in between. So, what is the delay occurring is the propagation delay. The third one is the queuing delay, which is the delay at the interface buffer. That is the major delay component. If we have a huge amount of data at the sender's end, so it is stored at the interface buffer and gets queued. So this is the queuing delay. So in general, the queuing delay is greater than the transmission delay plus propagation delay. Because in queuing delay, it has to wait for a longer duration of time till the transmission has been done and the propagation has done. So packet multiplexing in the network devices like routers, switches impact the queuing delay. So there is a certain capacity of the router or there is a certain capacity of the switch. So that particular switch or router, this is the particular switch or router in between A and in between host B. So it has a certain capacity. However, the data is coming at 10 Mbps, but it has a capacity of 2 Mbps. So it will queue all the data here and then only push the data after this has been sent. So how it is impacting the congestion? It is impacting if the queuing delay is increased. So there will be a congestion. So all the packets get queued here and they are starved here. And so the congestion arises. So more packets are incoming. So accordingly, the congestion arises. The third part, as we talked about, is the jitter, which is variation in end-to-end delay. So this is the steady stream of packets. They are going on a steady rate at 1, 2, 3, 4, 5 at a steady time. However, this is the same stream of packet, but after congestion or improper queuing. So these two packets have reached farther, and this is here, and these two are left far behind. So this is a jitter which is occurring. So it is end-to-end delay and it is varying delay. Every packet is delayed with different amount of time. So why jitter impacts the application performance? So this is impacting the application performance. Say, for example, you have video streaming, say in YouTube application. So you are getting certain packets with a delay of 10 seconds. If there is a constant delay, so those packets will get loaded and you will get a constant streaming. So, however, if you will consider the delay variation among the video frames, so one is coming after 1 second, one is coming after 20 seconds. So this is a very low quality of service which is happening in the video stream. And then the fourth case is the loss, which is a relative measure of the number of packets or the segments or bits that were not received compared to the total number of packets or segments or bits transmitted. So loss is the function of availability. So if a network is available, that is the capacity more than the demand. I mean, then the loss would be generally zero. So they have a lot of packets, like hundreds of packets. However, the demand is only for 20 packets. So this then the loss will be zero because if some packets are lost, there are still 20 packets which are in demand, which are received at the receiver end. So note that this assumption is not true for wireless networks because in wireless networks, there are some packets which are lost and they are still not retrieved at the receiver end. So congestion increases the data loss from the intermediate network devices. So what are the, now we'll categorize different applications, how are the different applications requiring different level of quality of service between delay, jitter, and bandwidth. So say this is a voice application which requires loss at the least. That means it cannot afford a loss because if there is a loss in the voice communication, then there is no meaning for a voice over IP or VoIP connection. So the delay can be less than 150 milliseconds. The jitter can be less than 30 milliseconds, and the bandwidth can be 21 kbps to 320 kbps. It is variable. So there is no restriction on the bandwidth. So then there is the interactive video where the loss can be less than 1%, delay again less than 150 milliseconds, jitter is less than 30 milliseconds, and bandwidth depends on the demand. Sorry, a second. Yeah. Then this is the streaming video. I mean, interactive video is the live video that we are talking about. Say now we are having a live session. However, there are streaming video which are already streamed in YouTube and they are displayed to you. So there the loss can be less than 5%. So there is a more stake at the loss, and the delay can be less than the buffer time. Then the jitter can be on the buffer time, and bandwidth depends on the demand. And then there is the data transfer, that is a file transfer. Here loss, delay, and jitter doesn't matter. However, best effort for the bandwidth is taken so that maximum possible data can be transmitted. I hope everybody is clear till now. Okay. So the formal definition of quality of service is that quality of service or QoS refers to the capability of a network to provide better service to selected network traffic over various technologies, including frame relay, asynchronous transfer mode, Ethernet, and 802.1 networks, SONET, and IP routed networks that may use any or all of these underlying technologies. So the primary goal of QoS is to provide priority, including dedicated bandwidth, control jitter, and latency required by some real-time and interactive traffic and improved loss characteristics. So how to ensure a quality of service over a packet switching network? So what are the needed from the net? What application needs from the network? We need to check that. How to regulate the traffic that enters the network, and how to reserve resources at router to guarantee the performance, and whether the network can safely accept more traffic or not. So as we've seen, the primary contributors to QoS are bandwidth, jitter, loss, and delay. So we will introduce a term flow, which we will use in this session. That is, flow is a stream of packets from a source to the destination. So what is the source to destination? Say machine to machine, a process to process, application to application, or socket to socket. So different flows require different level of quality of service. So why quality of service is considered at the network layer? So basically, we usually do the congestion control and loss at the transport layer. So maintaining quality of service requires both per hop and end-to-end behavior. So there might be the case when at the transport layer we can avoid congestion. However, there are still some services which are being controlled at the network layer, which needs to be monitored, and from there a quality of service check needs to be applied. So that end-to-end delay, end-to-end bandwidth, and end-to-end jitter, and total end-to-end data loss can be monitored. However, resource reservation need to be per hop basis because internally there are multiple routers and switches. So we need to monitor each of those routers and switches. So in the case we have monitored the overall congestion control, however, there is a packet loss at a particular router. So how do we monitor those and how to regulate the quality of service on those end? That is why it is done at the network layer. So those end-to-end requirements cannot be guaranteed in the network layer. However, that guarantee can be provided by the transport layer. So the network layer bridges end-to-end connectivity and per hop connectivity, that is the transport layer and the data link layer. Okay, so application classes based on quality of service. There are categorized into four different classes. One, as we have earlier also talked about, the voice require more orientation towards or more quality of services dependent over the this what uh, I forget the term. There is a loss, yeah. So if there, it cannot tolerate more loss because that voice needs to be transmitted without more loss. Okay. So for that purpose, we have classified it into four classes. One is the application which require constant bitrate, example telephonic application. Here the bitrate we not, need not to have a varying bitrate. So it requires a constant bitrate so that the voice which is being transmitted over the IP or network can be transmitted at a constant pace and it is received at the receiver end with the fulfilling voice mode. So if there is a more loss or more changes in the voice or there is more delay in the voice, that is not tolerable. Here, the bit rate will be constant. The second class is the real-time variable bitrate. So the depending upon the requirement or the live session, there is depending upon the bandwidth allocated or the loss allocated, the real-time variable bitrate can be controlled. For example, in the video conferencing, like we are having a live session, and in that time, what is the uh, properties of the network that we are getting, that is the network bandwidth or the delay properties. Accordingly, we'll have the real-time variable bitrate. Then it is non-real-time variable bitrate. Example, on-demand voice streaming, that is in the YouTube videos that you see. So it is not in real time, but a variable bitrate. The fourth class is available bitrate or best effort. So that means whatever is the best possible bitrate available, it will allocate accordingly. The application will work. So there is an example for this, that is the file transfer system, in which we require the transmission. However, there are cases there because at that time that might be disconnected or the network bandwidth is lost or the packet gets lost, so the data gets not transferred. However, that is not a major issue. In that case, whatever is the best possible bandwidth which can or the bitrate which can allocate the data transfer, that is the major case. So now we will see the basic quality of service architecture. I hope everybody is clear till now. If you have any queries, you can ask. Otherwise, we'll proceed. Okay. Yeah. So in the basic quality of service architecture, we have different modules. First one is the admission control, which talks about to ensure the new flows which are entered in the network only if the quality of service of all the existing flows according along with the new flows can be satisfied. Then we have the classification and the marking. Once the flow is admitted or the flow is entered, so then we classify what type of application is that and what is the type of quality of service which is needed by that particular application. Okay. So as we have seen the categories of application which are categorized, so based on that, like voice over IP or the file transfer or whatever application, based on that we classify the packets based on the application QoS requirements and mark the packets accordingly. Then third one is the policing and markdown, which monitors the flow characteristics and take appropriate action based on the flow QoS. And the other one is scheduling based on the markdown by the traffic policers, which schedules the traffic into output buffers on an interface. Then we have the traffic scheduling on queuing, which talks about maintain multiple queues at the interface. The scheduling mechanism services the queues based on the scheduling policy. Example, the priority queuing. So we have classified the application into high priority or low priority. So accordingly, the scheduling occurs, how the traffic should be monitored. So the high priority will be given first, or whether that scheduler should be preemptive or non-preemptive, that also happens for traffic scheduling. So one of the example is the priority queuing. So the high priority and the low priority. So firstly, the processes or the applications which are there in the high priority or the packets in the high priority queue are served first, and then the low priority queue occurs. So then we have the traffic shaping, which controls the outgoing traffic rate irrespective of the incoming traffic rate. Example, constant bit rate output from the interface buffer. So this is what traffic shaping is occurring. So say the input traffic is very bursty. So when that is going at the output traffic, it has a constant packet rates. So that means it helps to reduce the jitter. So this is what happens in the traffic policing. So this is the traffic rate which is occurring. And what does the policing do is the here, this is the policing, and it cuts the traffic which is above a particular threshold and then regulates the traffic accordingly. However, in the shaping, what it does is to maintain a constant traffic rate of a particular traffic. Say the traffic is above that particular threshold, so it tries to maintain a constant traffic rate of the outgoing packets. That is what shaping does. That is to avoid the jitter. So there are different say policies which are used for traffic policing. One is the leaky bucket. In leaky bucket, this is the type of prototype it uses. Say it has a bucket which is leaky at one point. So this is the incoming packets or incoming water droplets. The user action is to add water at a constant rate or at a varying rate. However, this is a opening or this is a leaky bucket which has a constant drip out. So the incoming packets are put in the packet queue. So the packet queue works as a bucket. So this is the bucket where the incoming packets are put. So a single server queue with constant server time is there. So if the bucket overflows, that the packet are then the packet are discarded. So this here the input rate can vary. So we can put more packet and less packet and at a certain rates, but the output rate remains constant. So this was the leaky bucket. However, there's another policy which is called the token bucket for traffic policing. So here the input packets are put in the packet queue. This is the packet queue. And then there is a token, a bucket of token, which has multiple number of tokens. So depending upon the tokens available, the packets are further transmitted or flown to the flown given for the output flow. Okay, so the token generation rate is R tokens per second, and the bucket size is B. That is the maximum token it can have. So the rate of output traffic is bounded by the token generation rate, which is that is the output rate is equal to minimum of PT. PT is the initial transmission rate and plus the or minimum of B plus RT. which is the flow according to the tokens. So, difference between leaky bucket versus token bucket. So, in leaky bucket, there is smooth out traffic but does not permit burstiness. And token bucket smooths out traffic and also permit burstiness. So, if there is no incoming packet, tokens are get added in the token bucket, and then the burst traffic is permitted to account for tokens accumulated. So if in leaky bucket, what happens if there is a bursty traffic that say if there are multiple packets that coming at a one go, all the packets are getting lost if there is above the particular threshold. However, but the incoming packets are also coming, but it does not allow burstiness. However, in token bucket, it allows burstiness. That means if there are in the output regulation, output traffic regulation, the leaky bucket doesn't help. So if there are burst of packet coming, but they are moving for the output, or their output is done at a constant rate. It is not based on the burstiness. However, in the token bucket, so when there is a burst of tokens arriving, a burst of packets arriving, and we have multiple tokens at the token bucket, then the all the packets can be flown as an output with that particular burst. So both the leaky bucket and the token bucket algorithms can be used for traffic shaping with addition to playout buffer, a buffer to add some additional delay to the packet that arrived so early. So I hope everyone is clear till now. So then is queuing and congestion avoidance. So we have studied these basic QoS architecture. And then this is scheduling. That is, firstly, we do the classification and marking. That is, mark all the data packets into different traffic classes. So the marked traffics are of different priority classes and requirements, require different level of quality of service based on their service level agreement. So higher priority delay sensitive traffic, that is voice over IP, high bandwidth requirements, that is this video live streaming, and best effort service, that is the data transfer. So there is multi-class scheduling, which is done. So we call them as classes of traffic. So traffic class 1 is the high priority data sensitive traffic. Then traffic class 2 is the medium priority bandwidth hungry class. And traffic class 3 is the lower priority best effort traffic. So different classes of traffic require different treatments. So traffic class 1 ensures minimum queuing delay of the packets. Traffic class 2 ensures sufficient bandwidth for the packets. And traffic class 3 has no specific requirement. It serves using the best effort services. So for this purpose, we used to have different queuing strategies. So now we have here we have different processes or different flows. So this is the classifier which classifies it into high priority, medium priority, and low priority. So this green ones are the high priority. Then this orange and the yellow ones are the medium priority. And then this somewhat yellow, light yellow, and then indigo and then blue are the lowest priority. So then we have the scheduler which schedules and queues the packet accordingly, and then to the further uh, to the further end. So this one type of scheduling is the priority queuing. So in priority queuing, there is an incoming traffic. Then the classifier classifies into high, medium, and low. And then the scheduler does a queuing according to the round robin manner. Firstly, the priority, this high priority queue, then medium priority queue, then low priority queue. So it transfers traffic from lower priority queue once the high priority queues are empty. So it is a non-preemptive round robin fashion in which it gives the priority queuing. However, there might be a case of preemptive round robin manner in which, say, for example, high priority queue is empty. So now the medium priority queue is traffic is flowing. So there again comes certain flow with the high priority. So the process gets the flow of medium flow gets preemptive. and then the high priority queue gets the highest priority, and the scheduler flows the high priority queue processes. So in that case, there is a starvation for the low priority queue or the medium priority queue. So that should not be the case. So that is why we use non-preemptive queuing. So then we have the case of custom queuing. That is, different queues are of different sizes, works like transmission window. Say we have a scheduler. So 0.3% of that scheduler is contributed for highest priority. 0.2 contributed for another uh, category of applications, and 0.5 is allocated for different types of application. So every type of application has a dedicated window and a transmitted window which supports guaranteed bandwidth to each of the different processes or flows. So then there is weighted fair queuing, which ensures fairness among the flows. That is, every flow will get equal amount of bandwidth. So queues are assigned with a weight, fairness proportion to the weight of the flows they have. So congestion avoidance, as we see, avoid congestion by controlling the queue parameters. So it is different from TCP congestion control. So congestion avoidance in network here is very much different. So TCP response on detection of the congestion. What is congestion avoidance? It ensures that the flow performance does not get affected by the congestion. So if the congestion avoidance is there at the network layer, we still need to have the congestion control at the transport layer. That is true. So why congestion avoidance is necessary for quality of service? So internet carries multiple data packets from different applications having different quality of service requirements. So there are two types of traffic. One is the elastic traffic and one is the inelastic traffic. So the elastic traffic here, TCP it is a TCP like traffic, which is elastic in nature of flow control based on the AIMD process. And in inelastic traffic, it is a UDP type traffic, which has a smooth or controlled or a constant bitrate traffic. So inelastic traffic is preferred for real-time application because here you need a constant bitrate and you need not to have a variable or elastic flow control. So for that purpose, for avoiding the congestion in the network, we use the random early detection, that is the RED algorithm. I hope everybody is clear till now. Yeah, you can have this PPT in the login page. Also, they are sharing with you the credentials of the links to the this access material. So that is on the drive. So you are, I think every one of you is getting that link also. So from there you can have this PPT. I'll upload there. Even if you want, I'll share at the end of the lecture in this chat only. Okay, so random early detection in this case, it drops drop probability if different from for different traffic depending upon the nature, that is elastic or inelastic. We need to drop certain packets. So red smooths out the drop probability across all the flows depending upon the congestion probability. So it detects the possibility of congestion in the network. And if the congestion possibility is high, it randomly drops packet before the NQ. So then it determines the possibility of packet drop by observing the average queue length. So here how it works, that it has the incoming packet, then there is the average queue length, then there are terminologies of max thresh, that is the maximum queue length threshold, then min thresh, which is the minimum queue length threshold. And then when we send the incoming packet, it computes the average queue length. Then if the this average queue length is less than the minimum threshold, then you enqueue the packet directly. However, if the average queue length is less than the maximum threshold and greater than the minimum threshold, Then it calculates the packet dropping probability. For that, we have a formula. If the packet dropping probability is high, then we drop the packet, else we enqueue the packet. Then there is a third case. If the average queue length based on the incoming packet is greater than the maximum threshold of the queuing length, then you certainly drop the packet. So this is what the formula is. Let dk denotes the packet drop probability and max p be the maximum packet drop probability. So dk is the max p into k plus minimum threshold divided by maximum threshold plus minimum threshold. So based on this formulation, we have obtained this plot. So if this queuing average queue, this is x-axis is the average queue size and y-axis is the probability. If the average queue size is less than the minimum threshold, then you enqueue the packet, then the dropping probability is 0. If the average queue size is between the minimum threshold and maximum threshold, so the dropping probability increase linearly based on the increasing average queuing size. And when the max queuing size increases above the maximum threshold value, then there is certainly a probability of 1 of dropping the incoming packet. Then the red ends virtual drop tail here. So this is the thing that how to regulate the traffic and avoid congestion in the network, and how to maintain the quality of service in the network here. So if anyone has any doubt till now, you can ask. I'll share the PPT with you now. It is of week 8. If anyone has any doubt in the meanwhile, you can ask me. Yeah, so the link, this PPT of this week has been shared. So for week 7, I'll be conducting the session on 24th. So now we will have a quick view of the possible assignment which you can get in the this subsequent week, which I think all of you have already completed as well. So please answer accordingly. So which of the following are the reasons that are affecting network's performance or the quality of service in the network here? We have just studied now. I think everyone is capable of answering now. Please answer the questions. I hope everyone is here. Please answer the question. This is very easy question. Which of the following are the reasons for affecting the network's performance? Okay, so the correct answer is D. That is, congestion affects network performance by reducing available bandwidth, increasing packet delay, and introducing jitter. So all of the above. The next question is, based on the quality of service requirement, video conferencing comes under which class of application? Constant bitrate, real-time variable bitrate, non-real-time variable bitrate, or available bitrate or best effort? Video conferencing. Yeah, please answer to that question. You have studied just now that the in video conference, it comes under which class of quality of service requirements? Okay, so the answer to that question is class B, that is real-time variable bitrate. So in video conferencing, we have a live video streaming and it requires real-time variable bitrate. So what is the transmission delay for pushing uh, a packet of size 1 MB through a network with a bandwidth of 16 Mbps? This is M capital B and this is M small b. So answer. Mm. Yes, the answer is 0.5 seconds and the network bandwidth is 16 Mbps. So for sending 8 MB of data, that is 1 M capital B equivalent to 8 small MB of data to the network, it will. So the question is, I think everyone is clear for this question. Okay. So next question is, the primary goal of quality of service is to degrade loss characteristics, control jitter, increase communication latency, or none of. for how long the mic was off? In which question was last told to you by me? I can re-explain those questions. Can any one of you mention? Or if it is fine, just let me know. Any one of you. Oh, question number 5. So let me wait. Let me repeat the other questions as well. Okay, so for question number 5, you have seen. Okay, fine. So now is that question number 6, that which of the following is not a benefit of traffic shaping? That is reducing network congestion, controlling the rate of traffic flow, improving network efficiency, or prioritizing certain types of traffic. Yeah, now the screen is shared. Yeah, so answer it accordingly. Okay, so the answer to this question is D, that buffering packets to smooth out burst of traffic is an example of traffic shaping technique. So it helps to ensure the network does not become congested with sudden spike in traffic. So next question is, which of the following is not a benefit of traffic scheduling? That is ensuring timely delivery of time sensitive traffic, prioritizing high bandwidth traffic over low bandwidth traffic, improving network efficiency, or reducing network congestion. Yeah, so the answer is B, that is prioritizing higher bandwidth traffic over lower bandwidth traffic is not a benefit of traffic scheduling. The next question is, which of the following is an example of traffic scheduling algorithm? We have just studied it now. Yeah, so the answer is A, that is weighted fair queuing. Then next question is, which of the following is not a benefit of leaky bucket algorithm? Controlling the rate of flow traffic, preventing network congestion, reducing the impact of bursty traffic, or prioritizing high bandwidth traffic over low bandwidth traffic. Yeah, so the answer is D, that is prioritizing higher bandwidth traffic over low bandwidth traffic is not a benefit of leaky bucket traffic. And then this is the last question, that using RED protocol algorithm in a network, the maximum queuing size is 100 and minimum threshold is 40 packets. What is the dropping probability of the current queue size if it is 70 packets and the maximum threshold is set to 90 packets using RED algorithm? Okay, so the answer to this is 20%. So that means the RED algorithm calculates the drop probability, as you know, based on the queuing size and the thresholds. So in this case, the minimum threshold packet is 40 packets and the maximum threshold is 90 packets. So the range is 50 packets. And when the current queuing size is 70 packets, so the midpoint range is 65 packets, which is 5 more than the midpoint. So using the curve which starts at 0% when the queue is at the minimum threshold and reaches 100% when the queue is at the maximum threshold, at a distance of 5 packets from the midpoint, the drop probability is around 20%. So the answer is A, according. I think now everyone is clear. So if anyone having any questions, you can stay. Otherwise, you can end the session now. Okay, so I'll stop the recording and thank you all for attending the session.